Welcome back, friends. Let's look into the spring force and spring energy. So this is a spring given to me. This is the equilibrium position of the spring here, and I'm going to change the color. So this is the equilibrium position, and from this equilibrium position, spring is being pulled in towards the right hand side direction. So the displacement of the spring is towards the right, so I'm going to consider the displacement is positive. And then when this mass reaches to this location, there will be some restoring force which will develop in this, which will try to pull it in the opposite direction. You guys will agree to that. So that's, I'm not going to name it as restoring force because it is trying to pull it in the opposite direction. I'll call it as negative. And then if the spring, let's say later on, reaches up to this point, so the spring is compressed now. So this mass at this point, the displacement will be in which direction? The displacement, because this is the equilibrium position, I'm measuring everything from this equilibrium position. The spring is moving towards the left, so displacement is negative. If the displacement is negative, restoring force will be in which direction? This restoring force which generated in the spring will try to push the spring in the opposite direction. So Fr will be positive. So what we can conclude by doing this small exercise, that when the displacement is positive, spring force is negative, and spring force is also restoring force. And when the displacement is negative, the spring force or the restoring force is positive. That's what we can conclude from here. And then we can apply the same concept to the vertical springs also. So if this is a vertical spring, and then I attach some kind of a mass to this. So this is a mass attached to this spring, and this mass will try to pull it in the downward direction like this. Because of the mass, the spring's gonna get pulled in the downward direction. Now when it gets pulled in the downward direction, the displacement will be negative, and the restoring force which will generate in this one will be positive, because that will try to pull the spring in the upward direction. So that's why whenever you see the formula Fr equal to negative kx, it means that the restoring force always gets generated in the opposite direction to the displacement. Okay, and now let's take a math problem on this concept. So a spring is hung from a hook of a ceiling. When the mass of 510 gram is attached to the spring stretches a distance of 0.5 meter. What is the spring constant? I wanted to find, oops, what happened? Did I make some mistake? Oops, I think I zoomed in too much. So the spring is hung from a ceiling. The mass is 510 grams. The mass given to me is 0.510 kgs also, and the stretch to a distance of 0.5 meters. So K value, we wanted to find out spring constant, and the displacement is 0.5 meter. So in this question, he's not telling us anything about the direction, although the direction is pretty obvious that this is moving in the downward direction. So we can consider it as negative from the equilibrium position. But he has asked us to find the spring constant. So I'm gonna solve this question once by using the direction, once without using the direction, and you'll find that the answer will come out to be the same. So let's solve it without using the directions, because spring constant does not have any direction. So I'm going to use the equation Fr equal to kx. So let's draw the diagram first of all. So there's a mass which attached to this one. Once I'm going to attach the mass, then the spring gets pulled in the downward direction like this. And then this is the displacement in the negative direction, which generates a opposite force Fr. And this mass, why this is pulling the spring in the downward direction? Because of the gravitational force. So I can say Fg is equal to Fr. So I'm going to compare these two forces, and Fr, we've already said it is equal to Kx. So Kx equal to mg. And then once I'm going to solve this, then this value, K value, I'm going to put the value 0.510 times 9.81 divided by, and this is x. Actually, I'll first of all put the value of x here, 0.500 divided this by 0.500, cancels out, 0.500, K value comes out to be 2.5 Newton per meter. Newton per meter are the spring constant units. So that's the value you're gonna get for the K. Now I'm gonna try and solve the same question using the directions also, because force of gravity is acting in the downward direction. So I'm gonna say force is mg, m times gravitational value is negative 9.81. This is really important. I cannot use the negative fg and then put m times, then again start putting the negative g value. So we can't use the two negatives again and again. Here I've already used the, either you use it in the force or use the g value as negative. You can't use both negative signs. So one for the force and one for the gravity. That will lead to the wrong answer. So same thing, K, this spring is moving in which direction? In the downward direction. K times, so this is moving in the downward direction. So I'm going to take this value as negative 0.5. So now dividing both sides by 0. Before dividing, I can take the negative sign as common. 0.5 equal to m times 9.81. Here negative sign outside, negative and negative cancels out, divided by 0.5, divide this by 0.5, and K value comes out to be again 2.5 Newton per meter. So we've already said that this is not a directional quantity, so direction does not affect the K. It'll always be a positive. That's the spring stiffness or spring constant value. So let's now look into another problem. Hopefully you are able to understand this one. So let's apply the spring force formula to the pendulum. So if this is a pendulum, when these are the extreme positions of the pendulum, somewhere here and here. When this pendulum reaches to its extreme position, then the restoring force will try to move it in the opposite direction, and the restoring force will generate it in this direction because it's a directional quantity. So I'm going to call it as this Fr. That's a restoring force, and then force due to gravity always acts in which direction? It acts in the downward direction. So I wanted to find the component of this gravitational force in again in x and y. So one of the component of this gravitational force is restoring force also. So if I wanted to find the component, I'll start making a right angle triangle here. So if I complete this right angle triangle, I can represent this restoring force here also, because of the collinear properties of the vector. If you don't know what is the collinear property of the vectors, you can see the videos from chapter number 1 also. So now this is the restoring force, and I wanted to write the formula for this if it is a right angle triangle. So FG, I wanted to write FR in terms of FG, because I can easily find out the FG value. So FR value will be equal to mg sine theta. That will be the restoring force developed when the bob reaches to its extreme position. Now let's look into some more concepts. Now we're gonna go to the spring energy. So we were talking about the spring force. Now we'll talk about the spring energy. So I'm going to erase this and make some space to talk about the spring energy. And then we will try and find the formula for the velocity, with what velocity the spring is, spring is moving, or the mass which is associated with this spring is moving when we pull it in the forward or push it in the backward direction. So if I pull it in the forward direction towards the right hand side, what do you think? What will be the energy stored in the spring? So you will say there are only two types of energy we've talked about. One is the potential energy, another is the kinetic energy. So potential energy in case of springs, it is also called spring energy. This becomes the spring energy, Fs. Whatever the role potential energy played in the previous chapter, when we talked about the mechanical energy concepts, that role will be played by spring energy, spring energy. Oops, not the spring force, spring energy in this chapter, ES. And kinetic energy will still remain the same. It is half mv square, and spring energy is equal to, again, we've talked about this in my previous videos on the springs. It is equal to half kx square. Sorry, not what I'm doing. Half kx square. Now, when the spring is pulled to its extreme point, up to this point, the velocity, it cannot move beyond this point. So the velocity of the spring, velocity will be equal to 0. When the velocity is 0, so the whole energy has been stored in form of potential energy, which is also called spring energy, which is equal to half kx square. So at location 1, at this location 1, if I have to write the equation for the mechanical energy will be equal to, again, potential plus kinetic. Same formula we are using as we've discussed in the previous videos. So potential energy, and because it's a spring energy, I'm going to write it as half kx square plus kinetic energy value will be 0. So mechanical energy at location 1 is this value. Now, when I release this spring, so spring will reach to this equilibrium position. So think about this. I would like you guys to take a moment and try to imagine this. As soon as I release this, what's going to happen? It will start catching the velocity. It will increase its velocity. It will pile up energy, and all of a sudden when it reaches here, and then spring will start pushing it in the backward direction because spring is getting compressed now. So it will start pushing, slowing it down. So at this point, you guys will agree that the kinetic energy will be maximum, because up to this point it is trying to pull it in the backward direction. The spring is trying to pull the mass in the backward direction. So I'm gonna observe this location 2. So a kinetic energy at location 2 will be maximum, whereas spring energy at the equilibrium position, this is the equilibrium position. So even if it is at rest condition, under rest condition, there is no spring energy. So if there is no spring energy, so what can I say? Spring energy or potential energy will be equal to 0. So at location 1, I can say it mechanical energy at location 1 will be equal to kinetic plus potential again. So potential will be 0. This I should name it as 2. I don't know why I'm saying it as 1. My apologies, guys. So this is equal to kinetic energy, which is half mv square equal to me at L2. So if, let's assume this is an isolated system. In case of an isolated system, I can say me at location 2 is equal to me at location 1. So we can say that this is equal to half mv square. I'm running out of the battery, so I'm going to move a little fast. Half kx square, and then I can cancel these two halves, and then mv square divided, not this, because I wanted to find the value of velocity. So v square equal to kx square divided by m. So velocity value will be square root of kx square upon m. Velocity is equal to xk divided by m square root. So that will be my final answer. And some of the books, they use the a symbol, a square root k upon m. A is just symbol when we using the word maximum amplitude, maximum displacement. Some books call it as the maximum amplitude also. So hopefully you are able to understand. I'll see you in the next video. Bye now.